All right, I want to welcome you back to Unit 15. This is acid-base equilibrium buffers. Folks, we want to talk a little bit about something called polyprotic acids. What do we mean by polyprotic acids? Well, we mean that there's more than one ionizable proton. In other words, in most acids, we're going to have, or many acids I should say, we're going to have one hydrogen that's going to come off. But polyprotic acids have two or more that will be removed under certain conditions, okay? So if we use H2A, for example, as the general formula for this polyprotic acid, that's going to have two ionizable protons, right? Two protons that could possibly be removed. So the loss of protons, again, occurs in a stepwise fashion. So let's take a look at these two equations here. We have H2A, and it's going to dissociate into H plus plus H. There should be a minus right there, folks. Fix it on your notes if it's not already fixed for you. HA minus. So we've lost that first proton in that first step. But then what's going to happen is the HA minus still has an ionizable proton on it. It's going to lose that proton in a second step. That H plus comes off in a second step. So we have to consider those two steps independently, right? Now, one important point about polyprotic acids is that once you lose the first proton, the next proton is much harder to lose, okay? It's lost much less easily. So that means that the acid itself becomes weaker and weaker and weaker. So let's take a look at a kind of a common misconception, and that is this one right here. We know that H2SO4 is a strong acid, right? H2SO4, sulfuric acid, is a strong acid. So let's just say that I were to tell you that you've got a 0.1 molar sulfuric acid solution and you want to calculate the pH. So remember that I told you that in order to calculate the pH, you're going to say pH is equal to minus the logarithm of the hydrogen ion concentration. The problem is, the question is, what is the hydrogen ion concentration? Well, some people are going to say, well, I know that H2SO4 is going to dissociate into 2H plus plus SO4 2 minus. And therefore, if the original concentration of the H2SO4 is 0.1 molar, the concentration of the H plus is twice that, or 0.2 molar. As it turns out, that's not correct, all right? That is absolutely wrong. And the reason is because of the fact that H2SO4 does not in one step dissociate into 2H plus and SO4 2 minus. H2SO4 actually dissociates into this, HSO4 minus, minus plus H plus. Let me fix that right there. Here we go. Minus plus H plus, just like that. So it dissociates completely into the H2SO4 minus, but once it does that, it's going to be a lot harder to take off that second one. So this is the one that happens. The one I'm showing in blue is the one that happens almost completely. As I'll show mathematically later on, this is going to happen. This second part where you have the second ionizable proton coming off is what I'll call mathematically negligible. Okay? Mathematically negligible. And I'll prove that to you mathematically in just a few minutes. Okay? So that's what I want you to keep in mind to start with. First of all, polyprotic acids are going to dissociate in a stepwise fashion, right? But you don't double the hydrogen ion concentration, because after you lose that first proton, you're not going to have a doubling of the number of protons. In other words, there's not going to be the loss, a 100% loss of that second proton, because even though the original acid was very strong, once you get to the HSO4 minus, that acid is not nearly as strong as the original H2SO4 was. Okay, so we've got that. Now let's look at a little bit of some acid structure, acid-base structure, and ask the question, what makes an acid and a base a base? Well, I've drawn an acid and a base, a strong acid, H2SO4, and a strong base, NaOH, okay? And what I want you to notice here is that there's similarities between these two species, right? Both of them, if you look on the right-hand side, have an OH, right? There's an OH here and an OH here. So we know that in this molecule, the OH comes off. It's a base, right? So it increases the hydroxide ion concentration. In this case, it's the hydrogen that comes off, right? H2SO4 is an acid. Why? Why does in one case does a OH come off and the other case a hydrogen come off? Well, it has to do with electronegativities, or I should say electronegativity differences, and where water will potentially come in and cause a break in a bond, all right? So let's take a look at the H2SO4. The electronegativity difference between the O and the H is 1.4 versus the S and the O only 1.0. So if water's going to come in, it's going to come in and it's going to break or dissociate right there. So if I have H2O just like that, it's going to come right in there and break that bond. It's going to dissociate there, allowing the hydrogen, I'll change back to a red color so you can see it more clearly, is going to leave. So H2SO4 is going to be an acid, a Bronsted-Lowry acid, because it's increasing the hydrogen ion concentration. It's releasing hydrogens into the solution. Let's contrast that with the NaOH. Here, the electronegativity difference between the sodium and the oxygen, 2.4, where the electronegativity difference between the oxygen and the hydrogen, only 1.1. So if water's going to come in, right? If water's going to come in, let me change the color again. I'll erase it first. Let's get it consistent here. I need a pen. Here we go. That should do it. So if water's going to come in just like this, then what's going to happen is that water is going to kind of attack right there. Okay? And that's going to make the OH then come off, just like that. The OH is going to leave. And so that's what makes sodium hydroxide a base, because OH is what it's leaving, and what makes sulfuric acid, H2SO4, an acid. Okay? So I just wanted to go over that relatively quickly. All right? I hope that makes sense. All right, I want to move on now to the strength of acids and compare the strength of acids. So you know that the strong binary acids are hydrochloric, hydrobromic, and hydroiodic acid. And you can remember them by I bring clay, right? I bring clay. Those are the strong binary acids. Now, why is hydroiodic acid a stronger acid than hydrochloric acid? Okay, it's an interesting question. And it has to do, again, with electronegativities, right? And electronegativity trends. I want you to think back to what we said about the electronegativity of the halogens, right? If you have a periodic table in front of you, by the way, that would be very helpful. Which has the greatest electronegativity between the three, chlorine, bromine, or iodine? Well, chlorine is highest in the in the family or group, and therefore it's going to have the highest electronegativity, right? That means that this chlorine is holding on to this hydrogen tightly, or at least more tightly than this bromine would or this iodine would, right? Well, what does that mean in terms of acidity? If chlorine's not going to readily release the hydrogen, that makes hydrogen chloride or hydrochloric acid a weak acid. If, on the other hand, on the hydroiodic side, if iodine is not going to hold that hydrogen nearly as tightly, right, then that's going to render this a strong acid, okay? The iodine is going to be holding the iodine not nearly as tightly, allowing that hydrogen to kind of roam away, get taken away by water, and therefore it's a strong acid. So if that's the case, what would hydrofluoric acid be? Let me ask that question. What would hydrofluoric acid be? Well, fluorine is extremely electronegative. It's not going to allow that hydrogen to go anywhere, right? So hydrofluoric acid is a very weak acid, just like that, all right? Okay, hope that makes sense. All right, let's move on now. I want to talk about oxyacids or ternary acids, and I want to explain a phenomenon and try to render an important reason for why we see something happening. So remember that oxyacids don't have the hydrogen directly attached to the central atom, so a different effect is at work here. There can be two reasons for the different acid strengths, so we're going to ignore the second one, by the way. Okay, so let me just go ahead and cross that one out. We're not going to talk about this right now. Okay, so but I do want to talk about this first reason, and I want you to understand why it is, for example, that 8ClO is a weaker acid than this 8ClO4. So this is the rationale. But before I do that, here's what I want you to remember. I want you to remember that the greater the number of oxygens, the stronger the acid. Okay? I'll underline that. The greater the number of oxygens, the stronger the acid. So if you just remember that much and don't remember the rationale, that's good enough. That's good enough. Okay? The greater the number of oxygens, the stronger the acid. All right, so what I've done is I've drawn on either side, I've drawn the weak acid, the HClO, or the weaker acid, I should say, HClO, and the oxygen is always attached to the hydrogen like this. And then on the other hand, on the other side, we've got HClO4, right? So that looks like this. And we want to try to explain why this hydrogen, right, this hydrogen is held so much more tightly to this oxygen than this hydrogen is held to this oxygen. Here's why. It's because of the fact that these oxygens here, if you have 3 oxygens as opposed to just one electronegative atom, what's going to happen is that these oxygens are going to pull electrons hard that way. They're going to pull it away that way. You with me? Now, what that's going to do is that's going to make this bond right here, this bond right there, very, very polar, thus making this bond right here very, very polar. Because if electrons are just being pulled in this direction, this bond right here is going to become very susceptible to hydrogen, to water attacking and dissociating that hydrogen. So that's going to make it very, very strong, a strong acid, because this hydrogen is going to be easily removable because of the fact that the bond next to it and the bond also that attaches the hydrogen to oxygen is extremely polar, rendering it subject to attack by water. Okay, so water will go in there and take out that bond and let the hydrogen roam away. Contrast that to this situation. Now, chlorine is definitely electronegative. There's no question about that. Let me draw an arrow like that, just like that. That's going to make this bond polar, but that's going to pull electrons this way, and that's going to make this bond polar as well. Right? So that bond is going to be polar as well, but not nearly so much. Chlorine is not going to be able to pull electrons in that direction nearly as much as these 3 oxygens are going to be able to pull the electrons in that direction, rendering this bond right here between the hydrogen and the oxygen very, very polar and susceptible to attack by water. Now, there you have it then. Why is it that the molecules that have the most oxygens are more acidic, are stronger acids? It's because the oxygens are pulling electrons away from the bond between the hydrogen and the oxygen here on the opposite side. That hydrogen-oxygen bond is not nearly as stressed by the chlorine as it is by the 3 oxygens. Okay? Folks, once again, this second rationale we'll just forget for now. Right? We'll just forget for now. And I think that's going to be about it for this one. I'll see you on the next one.